I thought since this is quite a diverse group and we don't all know each other, although we've gotten to maybe a little bit, I would just tell you how I ended up here doing what I do. And so I have started in math, proving, I didn't do anything besides prove theorems until I was a postdoc. And I've spent many, many years now working on biology, mostly in the immune system, transcriptomics kind of work. So I thought, as I was going through about how my background overlapped with things people have been talking about. And I spent a lot of time thinking about metric embeddings and discrete optimization and things in my grad school years, and then have recently worked on RNA velocity, which we had a momentary discussion about, and spatial transcriptomics and lots of other things that have been brought up here. And so most of the time, I overlap much more with things that people are doing. By the way, do I have to stand somewhere specific for this video? No, they don't. Do I have to stand back there?
Till here. I believe I'm not on the camera.
Okay, so I see. Okay, so I don't have to stand back there at least. I'm not good at standing in one place. So most of the time I work on things that are very related to things other people brought up here, even some TDA and things Smith has talked about. But today I'm going to talk about a project that is kind of out there for us, because Shmuel goaded me into it, basically. So, and let me just sort of say how it originated. It came out of a call by Welcome Leap, which is a nonprofit funding organization that does a lot of sort of large-scale projects in health areas and other areas as well. And so they had this program call a couple of years ago that was focused on identifying, developing, and demonstrating biology and healthcare applications that will benefit from quantum computers expected to emerge in the next 3 to 5 years. That I would never have responded to that normally, except that I happen, it's all about students and postdocs, and they talk to each other. There's a professor at U Chicago who's an expert in quantum computing, especially in the architecture and hardware side of things, and has a spin-off company that's local in Chicago. And so they were interested. And I also have a close collaborator in oncology. And then we started talking to Aram Harrow, some of you may know, at MIT. And so we just ended up kind of putting together this team. And one thing that I found to be much more true than I realized, it talks about the early days of any new computational method benefit from co-development of application, software, and hardware. And that's been really true. So we are actually doing things somewhat generically, like we're not building specialized devices, but we are thinking a lot at every stage. So we have been working together very closely at every stage: problem description, how we're going to design it, how we're going to do the algorithms, how we're going to do the compiling, how we're going to, I'll talk a little bit about some of the things that we get into. And so from a mathematical point of view, I think you'll find it very unsatisfying, because we take a very nice mathematical problem and then destroy it, basically. But I think there's some semblance of meaning left in that we're able to get some interesting solutions. And in my mind, when I came into this, well, let me tell you a little bit about the problem, then I'll tell you my perspective on why it was okay for me to do this, even though we're doing sort of neither math nor biology 100% yet. And also, I just want to be honest, this is the first time I've talked about this project. We are, it ends in 1 month. We're totally stressed out trying to get quantum computers to do stuff that we need them to do. And so I'm going to show you, up to a certain point what we've got, and hopefully there'll be even better results in a month, and you can look us up. But yeah, so this is my first foray into presenting on this. I also wanted to just give you, instead of doing this only at the end, this was, like I said, a very big team. So this is our fearless leader, Fred, but my co-PIs, Alex is in, he's a head and neck oncologist and also a trained statistician, and Aram at MIT, and Teague also at Inflection. So, and I actually know almost all of these people. I've been in rooms with them. I've certainly talked to them on Zoom. Like, we work very closely together, and I don't think there's any other way to do this at this point, to do anything kind of like this. So that's been probably the most fun part about this. Okay, so the problem that we decided to focus on is designing a hybrid quantum classical algorithm for biomarker discovery. And this is very natural because, like I said, I came out of discrete optimization. And so we're going to kind of be thinking in those terms as opposed to sort of other kinds of ways that you might try to do this. So generally what the sort of framework looks like is like you have a lot of patients, you get samples from them, all different kinds. Right now, we initially wanted to focus on DNA, so we can measure things like the mutations in their tumors, gene expression of their tumors, pathology images that get turned into featurized vectors by some AI model. And we, there are, of course, other kinds of data that we hope at some point to use. And the idea is that we would like to be able to do better at predicting things about these patients. Do they belong to a specific subgroup? Do they have a specific subtype of cancer? That would maybe be important to know about. The grail would be like, can we predict how they're going to respond to a treatment so that we don't give people treatment that they know that we can sort of guess they're not going to respond to, even if they sort of look at a very simple level like they might, right? We know that even many of our sort of indicators are not that great. And we don't have indicators for other people. So, that's kind of an important general problem in the area. So biomarker, measurable feature that indicates a clinically relevant state or outcome. We started with something relatively well understood. And we also focused a lot on the mRNA, on the gene expression. That might have been somewhat my influence because that's kind of a space I live in a lot, but it was also because initially we realized that they were just, for the sort of testbed problems we were working on, the mRNA was repeatedly way more informative than the DNA. So we just dropped the DNA for a while. And the pathology is like a whole other thing. I think trying to figure out how to load that onto a computer in a way that makes sense, onto a quantum computer in a way that makes sense is another challenge. So we'll get there eventually, but we sort of sidestepped that challenge temporarily and focused on the RNA for at least for now, and sometimes DNA. And so why do we want to do this? Like I said, we want to be able to classify. We want to know if a individual will respond well to treatment. I also think it's very helpful for hypothesis generation. Is there some reason why a patient is responding to a treatment? If we have a very complicated model that predicts that, it might be very hard to use that to guess at the mechanism and be able to test the mechanism. So if we have simple sets of features, we might have a better chance at trying to actually, develop theories about why they're not responding, test those theories, maybe develop targeted therapies to address that. And obviously, eventually, we want to be able to manipulate those who don't respond, for example, to be able to make them respond or change the therapies so that they are more responsive. And like I said, I'm mentioning this interpretable biomarkers. I think this word gets used a lot. I will say in this space, I think it really does matter. So the gap between what gets used in research, high-level, huge, complex models, what gets used if you have, a friend that goes to a clinic with cancer, it's huge, right? They get tested for some very specific things. Often those tests come back and say, like, we've got no information for you, or they indicate a treatment that doesn't help them anyway, right? It's pretty frustrating, honestly. And so, part of that might be because the big models are more likely to overfit. They're overparameterized, maybe. The smaller, simpler, more interpretable model is, the easier it is for somebody to take responsibility, the less expensive it is to deploy it. It's more directly yielding biological understanding, perhaps, like I mentioned. This is a real concern. It also happens to work well in this setting, right? So I think of what we're doing here as very complementary to sort of large-scale AI. It's almost the opposite, right? Large-scale AI is like take all the data and have the system learn itself what it needs to know. And here we're sort of doing something much more kind of fine-grained, simpler. We're going to build simpler models. And I think that they are both very useful in their setting. I also think the amount of data that we have, while it seems really large compared to what we used to have, it's still actually pretty small scale compared to like the world of data that other AI models get trained on. And that's something that we forget as biologists sometimes. I don't know, I call myself a biologist sometimes, so Okay, so the current biomarker approaches, some of you might know this, right? There's, like I just mentioned, we have these dense, highly parameterized models or very simple models. I think I went over a lot of this. I don't want to take too long. basically, these are kind of simple and don't perform that well. These have other problems that I already mentioned. And so our idea was that feature selection as a general outlook could address many of the challenges in these approaches. And I'm really sad Ben left, because Ben told me yesterday that he thinks everything is about feature selection. So I was so happy that he told me that. So I think it is a potentially very useful outlook. The reason that I found this interesting from my point of view, right? So feature selection is hard with classical computers generally, right? Sometimes we can do well with approximations, but it can be hard. So, why is identifying these sort of viable, multimodal cancer biomarkers hard? Why is it hard to find these specifically? Because, just because the generic problem is NP hard doesn't mean it's always hard, right? So, like I said, I think there's a relatively small number of samples. Often people will list large sample numbers, but then you go in and you realize that that's actually over many different arms or many different types or something like that. And once you dwindle down, it's actually like not that many samples on the level of individual. There's pretty complex interactions between all these different features, right? These are genes that work together, they do things together. They have all different kinds of partners in different systems. And so, if we ignore that, we're probably missing important biological signal. At least that's been a theory. There's big computational constraints, like I said. And I think here there's a high premium, like I said, both on interpretability, but also on accuracy, right? So as opposed to being super fast, it's maybe worth a little bit of cost, not our lifetimes, but to get something that's more correct. So that is maybe also an advantage of kind of this space. And then this is definitely a kind of a challenge for everything, but there's just a huge explosion of types of data that we can gather now. And so this gets to be very high dimensional in terms of features. And so it's kind of different from a lot of other scenarios where there might be more samples than features. Okay, this is probably familiar to many of you. So our approach was basically, okay, we're gonna start with data from public databases. I'll talk a little bit about the pre-processing that we do to make this more amenable. We're gonna do feature selection with the aid of quantum computers. So we use a lot of classical computing in all of this. We really just use the quantum computer for a few subroutines. And that's why this becomes like a hybrid kind of scenario. And then really the idea is to train pretty simple models using small feature sets and just see, can we improve the performance of those models? So we're not doing huge, complex parameterized models there. Stop me.
You're probably going to say this later, but so presumably there are, speaking as mathematicians, there's some theorems that say this particular subpiece that you're going to be doing is much more efficient to be done by quantum computing than by classical computing. Is that?
That's the wrong question.
Right.
You don't want to prove the lower bound that classical things can't do it. Right? Here you just want to go ahead and use the quantum computers to do something that looks useful.
I think.
Right? I mean, you don't want to have a theorem that's
Okay,
right? You don't want to get into P versus NP.
So I think there are. Let me say.
You want the lower bound.
This is actually a great and very relevant question, because what they want to show is sort of advantage, right? What they care about as the organizers is getting some notion of quantum advantage, a reason to use quantum computing over classical computing in today's world, right? And so I will say that there are theorems about things. Most of what we do, there is not any theorem one way or the other about whether it could give us or not give us. The actual algorithm that we use doesn't even have, it's a heuristic anyway. So we can't even prove that we're gonna get an actual perfect solution. Just give me 2 seconds. But I think we were going for two things. So one is we're thinking, okay, so from my personal perspective, I didn't actually care if we got quantum advantage or not. Because in my mind, if we do get a really interesting classical algorithm that does well, that's a win, right? That's a win for science. I'm happy. So, and we have learned quite a lot as we've been doing this, honestly, from the classical side. We actually have a guy in Fred's lab that is like our enemy. He's like in there programming the hardest, best, classical algorithms to demolish every time everything that we do. And it's great, right? Because we know, like, that's what we want. We want to know, what we could do if we just thought about it a different way. What I have found really useful, though, is that having this kind of framework made us think about solving these problems in ways that nobody is trying to solve them right now. And I think that's useful regardless of whether you get a quantum computing advantage or not, right? So what I learned from doing this is that there's a ton of information in very small sets of features. But we would never look for that, right? Because if you try to look for, small, it's still big, it's still hard to find a set of, say, 10 or 20 features, right, that are super informative among more of that. That's actually classically, it gets hard very fast, right? So you're either going to test them sort of one at a time, right, and just get a good set of features, or you're going to, fit a big model and use, 1,000 of them or 100, whatever. But this idea that there's actually information encoded in a good set, right? That's something in theory we know, but like we actually see some evidence of that using this approach. And I found it really interesting on the biological level, the fact that we see evidence that this is true. So that was, for me, a win, yes. Sorry, I don't know. Eduardo was first, sorry.
Yeah. Actually, you sort of already answered it, but so first of all, in this competition with your colleague, so far, these algorithms are beating the best classical algorithm?
So that is a good question. I think currently we're at a point where, we could, it's close right now, like the efficiency, we are getting into problems where it's getting harder. It takes much longer for the best algorithms to run. Okay. So, but it's still doable, for sure. We are using sorry. See, I knew if I'm on video, it's very risky for me. I'm way too blunt. We are using quantum computers that have a lot of error, right? So we're trying things on a few different devices, but by the way, this is now in a project also with IBM. So we're using, there's not a lot of error correction or anything like that. And the number of qubits, like they said in their thing, we are aiming for, 100 qubits, right? We're working with like 20, 30, we have small numbers of qubits. So we're really expecting that anything that we see where we start to pushing those boundaries is just gonna we hope that that's indicative of like a good advantage in a year.
The second part of the question was going to be, you could also do classical simulations of what would happen on a quantum computer.
Right. So we do. Yes, we do that, and that shows that looks good. Yeah. That looks good. That looks good. The hard part is mostly making it work in reality. And I'll tell you, we've done a ton of crazy things that actually kind of make it work. Yeah. Luis, right?
Theoretical theorem. There is like a whole study of the complexity classes that are the complexity class, sure, which is the BQP, the bounded quantum polynomial, which is the one that is going to tell you which problems are suitable problems for quantum computers. So in other words, I don't know if the audience is familiar with quantum computer or not, but it's not that quantum computers are going to go and solve any problem or anything like this. It's just some problems that could be hard could be solved by the BQP, the bounded quantum polynomial. Some others not.
Right, that was exactly. Yeah, that essentially was my question.
I mean, what is this complexity class? What are the borders, say, of this something that is under study, say? So this is even theoretically. Of course, there is some, for example, the factoring some primes or the groups, algorithm. All these two in particular are two examples in which you can see that there is a quantum advantage theoretically. So far, there is like no practical.
And also the new cryptography, this new quantum cryptography standards, right, or things that cannot be presumably.
Right, and the second question that I want to make is that
which are called same as.
Right. Same as currently, different hopes, yes.
Comment and question that I wanna throw is just like quantum computer people think of, in the sort of from public science that they're gonna come and solve all combinatorial problems. This is actually not the case. It's quantum computers are not gonna work in this way. It's like parallelizing all possible options and go and work on them. This is not the way a quantum computer works. And actually, for data kind of driven problems, quantum computers may be very problematic. Why? Because you can't store data in a quantum computer. So each time that you want to use data And a quantum algorithm, you have to transfer the data from a classical computer, say, to the quantum machine, do an operation, you absolutely kill the system because you get one solution, go back and forth, right? So the bottleneck for the complexity of the problem is going to be on the transferring huge amount of data back and forth, right? From the classical to the quantum. So my question is, to what extent data-driven problems do you think are good problems for quantum?
So there is a question in there. Okay. So I think, right, I fully appreciate that. We actually chose to load our data in a pretty simple way, so we don't struggle as much with the data loading, but what it means, and we don't do massive problems, right? We're doing really the kind of problems where the search space is huge, but the problem description and the solutions are pretty small, relatively speaking. And I think, I don't know, honestly, like, people have not shown either way, right, that this is gonna be, a place where we're gonna get advantage. I think what it looks like is that we may be able to find better solutions now, maybe, but the notion of an empirical advantage, right, is that there's kind of an arms race as it goes forward, and I don't know how that ends up. And on a theoretical level, I don't know. So, and I don't think it is known for many of these problems. Not to say that there isn't, complexity classes in theory, but I don't think they've come down on this. So I can sort of talk about like where we're trying to go, but I think in a lot of these cases, what's hard is more the optimization, right? It's the fact that are you going to run into like a plateau where you have no gradient? Are you going to, is it going to be too noisy? Do you have like the kind? There's a lot of other issues that we've run into. That problem hasn't been so much the loading and taking off. So I think it really depends on in which problem space you're focused. And here we ended up focusing more on smaller problems with the hopes that we can actually get to something bigger. And I will say, like, even when I sort of mentioned this, people are like, they come and they say, oh, I have like, 500 genes, or I have even 100 genes, right? And I want to get this down to 10 so I can go make a little chip, take it to a clinic, and we can actually do this cheap. And so even being able to do something like that, or to understand which of these genes actually matters, so that you can, think more about the biology. I think there are really use cases for relatively smaller problems for now. I can't promise forever. Okay, does that help at least, Jess? Okay. All right, so let's see. Right, so the ideas here that we're going, oh, maybe I went off camera. We're identifying, kind of small, highly informative, multimodal set of K features. And we're going to formulate that by optimizing third order, sort of, I'm using approximation in the loosest sense of the word, not in the formal sense of the word, which I'll explain. Third order approximation of mutual information between the features and the class labels that we're trying to predict. And then we're going to train a model. So this here is all classical. Eventually, we'd like to get into more QML kind of ideas. But right now, we're just doing this part, quantum, and this is classical. And like I said, right now, we've been focusing on a pretty simple, this is just to say that we want to go to more complicated clinical biological endpoints and also more complicated data sets. We are not doing that right now. This is my very ambitious colleague's slide. Okay, so our current setup is, let's say we're using public data. We've got M patients and initial features. And because exactly of this problem of loading data that we kept pretty simple, we have to kind of focus on small sets. So we actually do some kind of enrichment sampling to try to pick a reasonable starting set of features. And we do this for lots of different problems just to see if we can still get somewhere that's interesting from that. And what we're looking for is a subset that builds an interesting model. And there are actually plenty of times where the full set, it's not all the time, but the full set of features actually does worse than the subset, right? Because the full set overfits. So we see real concrete evidence of that, even from going from like 20 to 10, which I was kind of surprised by. So it's, there is actual sort of value in understanding what really matters when you go try to predict in a totally different set of patients. So we're using patients, all of our training from TCGA. It's a very well-known cancer database, and we're testing, the final testing is almost all being done in a different database. where we chose 9 cancers that are overlapping in both. So we took patients that have, cancer types that exist in both. And our target label is basically the prediction of which cancer type. So this is a pretty well-known problem. This is not going to, solve cancer problems for actual patients right now, but it was a good test bed because it is somewhat understood. We expect to have some signal there. If we can't do this, we're not going to be able to do other things. We did just start looking at actual predicting treatment response from other data, and we're getting some interesting results from that just now. That like I think my student sent them to me this morning. So yeah, I will try to show that.
So your goal here is to figure out the primary cancer and where the origin is?
Yeah, exactly, to figure out the primary, exactly. It's a pretty well understood problem. Okay, so we can think of each patient as a sample of the joint variable. I have no idea what time it is. I need clocks in the room. Okay, 11:11. I'll try to give you a tiny bit more. Let's see here. So each patient is considered to be a sample of the joint variable, right? We have the label of which cancer and then say the values of the gene expression. We realized right away that one of the ways we could make this data more loadable, to Luis's point, sorry, I say it like I have a colleague who's from Portugal, sorry. So to his point, to make this more sort of tenable, we thought, okay, well, let's just bin these into quintiles, right? So we take the transcript counts and we bin across per gene, but across all the patients into quintiles. And we initially thought like this will be very lossy, but it's the best we can do. It turns out I think this is probably actually a very useful pre-processing step in many applications because, it's very hard to predict whether you go up by 10 counts or down by 10 counts, right? And so having bins is actually kind of helpful for removing a lot of noise. It probably misses subtle signal when you have enough data to understand it, but I think when you don't, it's actually kind of helpful. Anyway, that's what we do. All right, so our problem at a high level is we want to find a set of K sort of features in that set of N that maximize the mutual information with the target label. And that's our way of formulating that is basically instead of saying, okay, we're going to fit a specific model downstream, let's just maximize the mutual information, you use whatever model you want downstream. We do also test downstream simple models and look at their performance. So this is a pretty well-established model. It's been used for many, many years in computational biology and lots of other areas. It's been used to increase the relevancy of features, reduce the redundancy among features. And so, of course, it's complicated to actually compute that. So the first question we ask is how can we make this a little bit more feasible? And this is where we start throwing math out the door. So here we go. Okay, so first thing we do is so let's say we can write this mutual information in terms of the entropy and the conditional entropy, right? The entropy of the set of features minus the conditional entropy when you know the label. And if you have if you can partition your features into, say, some L subsets, you can use this chain rule of entropy to basically, write this as a sort of telescoping conditional sum. And what we were trying to figure out, let's make an assumption here, right, that we don't have super high order interactions. We might have them, but we're just going to assume that we don't. And we felt totally comfortable doing that because most methods do at most single mutual information. Maybe they look at order 2, right? So we're if we go up to order 3, we're already doing far more. We don't even know if that's worthwhile or informative. So let's just assume that there's not more than that. If you assume that there's not, more than that, what does that mean? Mathematically? So it basically means that, there's some partition where this is actually equal to that, right? Where you can actually just write it as a sum of the individual sets. Okay, but we don't know what that partition is. So we do another thing, which is we just average over all the triplets, right? Okay, so if somebody has an idea about a better way to approximate this, I would love to hear it because this is almost definitely not actually a great approximation, but it's reasonable starting point. We did lots and lots of analysis to try to understand how reasonable, empirically at least, and it seems to work. I'll show you an example. I just wanted to sort of finish this formalization so we can talk about this as essentially we can turn this into a polynomial constrained binomial optimization problem, right? Where we have these costs, which are the mutual information on the triplets, and this generalizes spin glass models that are pretty common, and we can write this then as like a Hamiltonian. I guess I don't know where my word Hamiltonian went, but we can write this as a Hamiltonian, so we're trying to minimize the energy of this Hamiltonian now. So this becomes very amenable to all the methods in quantum computing literature that are really designed for, integer combinatorial optimization, the field of my PhD, right? Combinatorial optimization. So there is like a kind of few lines of work in the quantum computing algorithms literature that have really kind of been devoted to developing methods that should work well in combinatorial optimization problems. One that we're going to focus on here, exactly because of the fact that we hope that it would actually give advantage in near-term architectures as opposed to sort of in the distant future, is this quantum approximation optimization algorithm. I think this name is hilarious, because can you imagine if we had like the equivalent in classical computing? It would be very funny. Anyway, so but everyone calls it QAOA. And we basically develop a variant of it that keeps many of its attributes. This is a heuristic. It's not, proven to solve, to find the minimum energy. It gets an approximate solution. And we're going to even go beyond that in terms of the approximation. So I just wanted to go back and say that...
One thing is, don't you have an approximation to the energy or the approximate to the R in the energy? Right? I mean, you find
so good. So it's an approximate... I think, actually, when you sample, you get the energy. So I think it's an approximation to the energy, and that's to the minimum energy. So you find, but from the measurement, right? You have, you can, like when you do the measurement, you're going to figure out what value gave you the energy. It's just not necessarily going to be in the minimum state, the minimum energy state. Does that make sense? Like you won't have yeah, okay. So, sorry. Yeah. Okay. Anyway, so here, this is just to show that we did, we actually tried to compute empirically MI and look at how it correlated with this H-cubo formulation. These are really small problems because it's hard to compute empirical MI. And so we generated a lot of them and tried to kind of look at the spread of correlation. And in general, here it looks pretty good. We also did lots of other kinds of testing, just looking at the accuracy and prediction. Like, I think it's a reasonable starting point, although it's clearly not, a perfect proxy. Okay, so we have probably insufficient time. When do I have to stop? I don't remember what time it is.
Well, we can steal your
You
time.
have 7 more minutes and then 10 minutes of questions.
Okay, 7 more minutes.
So you have 17 more minutes.
Yeah, well, I don't want to get in the way of questions, but I'd much rather be interrupted than have everyone stare at me silently. So yeah, much rather do it this way. I found this impossible. Like I cannot teach you quantum computing. I barely understand what I'm doing. But I also want to show you a little bit of the algorithm and of all the things that we do. So to be able to do that, I'm trying to give you at least a very high-level view of what it's trying to do, right? And I'm not going to do, I feel like the way that I learned a lot of the theory was not actually very helpful for understanding algorithms. So I'm trying to give you the version that I think I would find helpful, which may or may not, your mileage may vary. Right, who here knows at least the first 2 lines of this? I'm just curious. Everyone, okay, great. So you should have told me that. I got very nervous for no reason. I thought, okay. So we have a qubit, states, classical state 0, 1. Superposition is basically a combination, linear combination across the states. When we measure, right, we can measure with probability equal to the absolute value, the squared entry of the quantum state vector. Okay, so the operations on the quantum state vectors are represented by unitary matrices. And that's like the thing that Shmuel said is all I need to tell you, which you apparently might already know. So the way that I think about this is like the quantum algorithm, the way that we're using it, it's basically we're preparing a state, right, and then we're sampling from it. And we're preparing a state and sampling from it, just like, like Luis described. And we're going to do that actually quite a lot so that we can actually get a sampling of a pretty complex distribution. That's sort of how we're using it. So the
preparation of the state, I'm sorry.
So when you prepare the state, you apply a bunch of these unitary matrices. You're basically, okay.
But how many? I'm sorry. How long an evolution?
Okay. So that depends on, so I meant sort of as a generic framework, you can think about that. In this specific framework, we're going to do p times. So this is a parameter of the algorithm. And so the algorithm basically, this is a by quantum computing standards, classical algorithm. It has like basically two, or well established, it has basically two parts. You have one part, which is that you encode essentially the cost function of your actual, optimization. So that's this cost Hamiltonian. And then you have a mixer Hamiltonian, which I, have yet to fully understand exactly how it works. But from what I understand, it's sort of like a perturbation. Like essentially, I know what it's actually doing, but I think it's useful to think about it as kind of a little bit of sort of mixing stochastic sort of perturbation so that you don't get stuck in some kind of, eigenspace or minimum, local minima or something like that.
Are the sigmas random variables?
No, sorry. These sigmas represent the poly operator. So it's a bit flip. It's like going from 0 to 1, 1 to 0. So essentially you do kind of a cost, and then you do sort of this kind of parameterized by this angle beta, you do some kind of mixing along these bit flips, and then you do a cost. Then you apply the cost Hamiltonian, and then you do the bit flip. So you do this, and the number of times you do this is a parameter of the algorithm. It's p. Why this should work, I honestly, this is the part where I need my colleagues here to defend this. But go ahead.
So can I see the number of qubits either this way or this way in this diagram?
This way. Yeah, this way. Yeah. So and basically this depth, right, in the kinds of settings that we're looking at is very small, right? We basically cannot get, so if you can go bigger depth, it's, more powerful, but it's also way more complicated, and you have all kinds of error that builds up, and it's just, so we're thinking very low depth.
So what is, sorry,
yeah.
In a real, I have no clue how this is implemented on a real IPM quantum computer.
It looks like that actually.
So this evolution, right?
Yeah.
One of these unitary operators.
Yeah.
Happens over how much real time?
I have no idea. Less time than I can think about.
Okay, but there's some clock that until I do the next mixing.
In theory, but I don't think that that's important in this algorithm.
I have no clue.
No, I understand, because you're thinking of the evolution of the system, so I understand that. I think, right, so I think it's, here I think of it really just like a bunch of matrix operations where I don't think that that we're actually using real time here as part of the
something is being done, right?
Right. So you're doing.
Parts,
what'd you say?
Something is being done p times.
Something is being done p times. You're applying a unitary operator,
right,
followed by another unitary operator, right? And you're doing that p times. So
how much time in between?
I don't know. Yeah. I don't know. I don't think of that as a parameter of the algorithm. I don't know if it matters, honestly. I think you try to do it, I don't think this is, the real time here is actually, okay. So I'm sorry if I'm honestly, this is like not, I'm not a physicist.
Partly because you're taking p to be relatively small, so.
Right. These are tiny, this is like tiny. So this is not slow to run. The whole thing is a pain. So the reason this becomes difficult is, from my point of view as a computer scientist more, is that you have to fit these variational parameters, which are these angles that are actually part of the unitary operators. And to optimize those, essentially you take a measurement and then you try to change the variational operators just the same way you would do it in sort of a neural network or something, except that this is expensive, right? It's a variational quantum approximation algorithm. And so
but you're collapsing in between every time, right?
Yeah, I mean, you put these new ones in. It's not even, wouldn't even matter because essentially these actually change, right? Because these actually become new unitary operators the next time you go around because they're actually functions of these variational parameters. So you're changing the inputs actually. And so one of the ways that people have tried to solve this is by doing what's called recursive QAOA. So we just get longer and longer acronyms. It feels like I'm back in immunology. So it's RQAOA. Yes. What's your name?
Katie.
Katie. Hi.
Do these variational parameters, is this like directly related to the features that you're selecting?
It's no, I mean, in the sense that it's a parameter of the algorithm, it's related, but it's not direct. It's just sort of influences like what the angle is of the like this is you can think of this as an angle, right? If you write this as like cosine whatever plus, so this is a bigger, if this is bigger or smaller, it changes this unitary operator. Honestly, so let me just say that like I think of this a lot as black box kind of things to the extent that I can, because otherwise I can't do anything. So I'm not the best presenter, but your questions will help me, learn more as I go. So the main thing that the recursive part of RQAOA does is it says, okay, instead of trying to do all of this, I'm going to use this sort of a shallow QAOA, and I'm going to just try to fix one edge. So an edge here is really like one of these. I'm going to try to decide, are these going together? How do the variable settings of those relate? You can think of an edge as being the setting of those three together, like a multi-edge kind of thing, right? So instead of an edge being just between two nodes, now it's, between these three.
Learning the coefficient, the CIJK?
No, so I should say the CIJK are things that we compute expensively, classically ahead of time. So they are kind of an expensive part of this computation, so we know those. What we're learning is basically the settings of these, whether we're going to include or not, right? And so when we set an edge, it's not a final decision, it's kind of a decision on the triplet, right? How do those triplet go together? And so basically what our QAOA does is it makes it does this whole optimization, but just to pick one edge, sets that edge, and then the problem is reduced, reformulated, and then you do it again. And basically, after a couple of those decisions, you have a smaller problem. And because these are sort of problems that grow a lot with, extra choices, right? They get much more complex. Actually, just doing a few steps of that recursive problem can bring us, down from a place where, you couldn't consider it classically tractable to a place where you could consider it classically tractable. So as soon as we get into the place where we think, okay, we're in a small enough problem size, we then use our like best guy's classical algorithm to solve it. So that's so this is why like as this gets better, this moves up a little, right? That's why this is kind of a shift, because it's actually sort of a race even within our own group, right? It's like where that trade-off is. But we know that that's always going to exist. At some point, there's going to be a trade-off where we're not going to be able to give a bigger problem. And it's not that far off from where we are. So there's just a couple more points. I think almost done on the. So I just wanted to point out in case people are interested, I found it interesting to understand all of the other things that we could do to try to make this function. So like I said, trying to do this parameter, finding your initial setting of the parameters is actually really hard. So one of the techniques, it kind of involves solving a smaller version of the problem and then using the parameters that are optimal for that as if they were working in the larger problem, which for some reason often seems to work. There's some sort of concentration in patterns. And so, and that actually gives us pretty good savings. It's like kind of incredible how well it works, which could mean that, maybe these problems aren't as hard as we think they are. Like, we're not sure exactly what it means that we have this level of parameter concentration, but it gives us a way of kind of choosing parameters that reduces all the work that we have to do to find them. The other thing that we do, sorry to show, this is kind of a horrible slide to show. Nobody wants to see a bunch of graphs like this, but But I just wanted to say, because I didn't have a great representation of it, that another thing that we do that's made a huge difference actually is basically we realize that, okay, we have this complex problem, right? That's the full specification of the problem. And it turns out that you can just start throwing out parts of it, what we call problem sparsification. You just throw out constraints that are in the problem, and you can actually maintain a pretty good solution because a lot of those constraints are just like either redundant or irrelevant. And we do it in a way that is aware both of those coefficients, right? So if they're lower, if the coefficients are relatively small, then we're happier to throw out the constraints. We think they're going to make less of a difference. But there's sort of a way to do it that doesn't just take into account the problem description from the theoretical point of view, but also takes into account the actual architecture. So when we were thinking about doing like a hexa, I mean, it's crazy because I don't know about any of this. We're used to thinking about things being able to talk to each other in really complicated ways, but one of the problems in a quantum computer is that which bits are near each other matters a lot, and how many qubits are near each other matters a lot. And so in a hexagonal structure, you've just got like these rings of 6 kind of that are near each other. And so you can try to sparsify your problem so that you get rid of constraints that would be really hard to encode, that would use up more of your qubits, and keep ones that are kind of near each other more, for example. And we're moving that away from just the hex encoding, but doing other kinds of sparsification that try to take into account some notion of the actual architecture. So that's just an example. And what we see is that we maintain pretty good solutions for quite a lot of, we can get pretty good sparsification for some of these problems. We don't know how that scales, but we're using this actively even on the classical side now, right? Because we're like, okay, if we want to try to solve things, why don't we just throw out, 50%? We can run problems that we thought were way too hard, and now we can solve them using a classical solver, and we can at least look at the solutions and see maybe they're still better than any other solutions that we have with other means. And that's actually working fairly well. So that's an example of a kind of approach that we would never have had if we hadn't thought about how to make this run on a quantum computer. Okay, so last 2 minutes, I just want to show a couple of actual results. Again, sorry for the kind of horrible plots, but so here, these plots each show an evaluation of, basically we generated, say, 1,000 different problems of 20 subsets, 20 feature subsets from which we were trying to choose 10 good ones. And we're just trying to actually do this 9 sort of class prediction problem, right? And we're using, because these are kind of unbalanced, we're using balanced accuracy, or we used F1, some notion of performance that takes into account the class sizes. And then we used actually this very kind of it's not simple, but it's like a fairly established method, feature importance. It's really quite good at picking good feature sets. But we also use lasso because, reviewers want us to, program managers want us to use lasso and other things. So we tried to use a bunch of sort of classical feature selection methods. And then we were evaluating, right? Remember I said our downstream model is separate. So we then take our feature sets that we find with using these different methods, and we just evaluate how well they perform in terms of predicting the cancer of origin using, say, a regression model or a SVC, a support vector machine type model. And here we have entropy QBOS performance on the y-axis and these other methods on the x-axis. And I have no idea what is the difference between the top and the bottom right now. I'm sure it's something very meaningful that is not marked here. But anyway, these are all different sort of methods of evaluating. Probably one is balanced accuracy and one is F1 or something like that. What we see for many of these is that this sort of increases as we get to bigger problem sizes. So these are pretty small problems. We've been sort of building up the data for larger and larger problems as much as we can. And what we see increasingly is that, like here, you see there's like a few problems where the best methods don't do great, but we can actually do pretty well. And this becomes sort of pronounced, right? So like a lot of the time it's 6 of one, half a dozen of the other. We're doing kind of as similar to a classical method using this quantum method, but there'll be a lot of problems where the solution looks very hard, like they don't find a good solution classically, but we actually do very well. Like we can actually get pretty good prediction by choosing a better subset. Yes?
Sorry, I'm just having trouble reading these graphs.
Oh yeah, me too, yeah.
The x and y axis, what is the y equal?
So I'm so sorry. I try so hard with my students to get them to label correctly. They're wonderful, but labeling is another thing. So one of these, I am sure that one of these is either, so it's the same thing on the X and Y. It's either balanced accuracy or F1, both measures of performance. And I don't know which is which. Maybe I cut it off myself when I put it in here, I don't know. We have, so the performance of entropy cubo, our method is always on the y-axis. And so essentially if we're above that dotted line, we're doing better. It's kind of a visual.
What is each brown dot?
Each brown dot is a specific problem that we generated where we were saying, okay, among these features, can we find a subset that predicts well? We don't necessarily expect to do well. Like some of those features might just be crappy features to predict from.
So I'm still confused about comparing to the classical algorithm. So
yes.
Classical algorithms, you got this huge combinatorial problems, right? So
we're giving it the same problem. Right. We're giving it the same 20 choose 10 or whatever 30 choose 10, just to be clear.
But you could presumably run this longer with more different initializations.
We do the very fairest, bestest thing that we can for all of those.
But any resource constraint that is the same for both?
I mean, when
why allow you to use cluster?
So let me just show you. Like here, basically, we did give cutoffs, right? Because here we're looking at a method that actually gives a proof of a gap, right? And so that's a specialized kind of like we can, when we can get a proof of sort of the gap, then it's worth running for longer if we can get that. But in these, we're not. That's for like how well we solve our problem. These are just like if you were a biologist, you wanted to find you would run this and they stop. Like I can run it doesn't change. Like they have their own stopping points. They have their own way of, they have their own optimization criteria. They reach some point, they stop. Like these aren't methods where, you could sample for 1 million more years or something like that. They have their own. Okay, yeah, sorry. Let me just say, this is not, I want to show 2 things in 30 seconds each, no questions. So this is just me 6 months ago trying to start getting into these, but now we've done so much more, I have to do it more. But we were just trying to say, okay, when there's a difference of say even 1 or 2 features between what we choose versus another, why? Like, can we understand anything about what features get picked in one case or another? And so one of the things I looked at is just, kind of what it looks like is when there's a difference, it's often because there's a feature that has high individual mutual information, but it doesn't really collectively add a lot with others, right? Which is what we would hope for based on what we're trying to do in our method. So for example, we might see like a classical selection picks this individual high effect gene that's a chromatin binder, histone binding, and we pick this weird gene I've never heard of, but it turns out that it's in a lot of other triplets. It has pretty high it increases the mutual information in sort of the sense of other sets getting better, right? So that's something that's very hard to judge with a classical method. I have to do a lot more of that. That's not meant to it's meant to show you a kind of what we would like to try to do. It's not systematic. And this is just the thing I said came in. I have to show it because otherwise my poor student will be sad, which is that we've taken data from a very different study here. So now this is a kind of seminal breast cancer study. And we isolated a group of mostly triple negative patients. There was, sort of isolated in the PCA space, not necessarily all classified as triple negative, but predominantly. And we took a sort of set of biomarkers that was used both by them and by a bunch of follow-up publications. These 23, there are 27 genes, but only 23 of them are relevant for this subset of patients. And we just asked, okay, so instead of evaluating them one at a time, which they did, right? They looked at the p-value association in a logistic regression model. Can we actually do something interesting by looking at subsets of these? So suppose we allow ourselves to pick 10 of these genes. Can we get interesting predictions from that? And we get some groups that predict very well balanced accuracy. And here we're not predicting what kind of cancer. We know that, right? We're predicting a complete response, right? We're predicting a response to treatment, whether the tumor actually responds. Now, of course, this can be completely overfit. This is a cross-validation kind of, we're trying our best not to overfit. But the idea is that we'll go back and sort of use these collections, right, to try to predict, to try to improve sort of what scheme you would use for treating the patients, which is the way they get used in the literature, to see if that would actually potentially improve the response of patients if we could have sort of reimagined doing the study. So that's a way of judging that. And we see quite interesting kind of results there. So far, this is very early. Like I said, I don't want to overinterpret it. But this is just the balanced accuracy here and the sort of negative log p-value here. So we're saying we do see some pretty good performance. They don't even report the effect sizes for theirs because I don't think they're very strong. They're just statistically significant. All right, there's my group. Ryan, guy who did a ton of the work on the classical side, also works really closely with the quantum computational people. Shmuel was on his committee, and he had lots of other projects as well. He just graduated and is doing a postdoc. Sophia is a great assistant in my lab. And then again, here's all the people. All right, thanks for all the questions and discussions.